Imagine walking into a mosquito the size of your arm. Then realize that mosquito would be the small guy in town. Welcome to the Carboniferous, the true age of giants. Forget Jurassic Park. Picture a forest where a single bug could block out the sun. Imagine a world where dragonflies, not T-Rex, were the most formidable aerial predators. And millipedes, longer than a car, rumbled through primeval undergrowth. This wasn't some fantasy realm. It was Earth, roughly 300 million years ago, during the late Carboniferous and early Permian periods. No T-Rex, no Triceratops. Those titans were still millions of years in the future. Instead, colossal arthropods truly ruled the planet. How did insects get so terrifyingly huge? And why did that golden age of gigantism slam shut? Stick around, because the answers to these questions rewrite a fascinating chapter in the story of life on Earth. So, how did these creatures get so enormous? Well, back then, Earth's atmosphere was drastically different. The air wasn't just a little richer in oxygen. It was a supercharger. We're talking about oxygen levels around 30 to 35%, almost double today's 21%. Why does that matter for bugs? It all comes down to how insects breathe. They don't have lungs like us. Instead, they rely on a passive system of tiny tubes called tracheae, which branch throughout their bodies. Oxygen diffuses directly from the air through these tubes into their tissues. Think of it like this. The more oxygen packed into the air, the farther that gas can efficiently diffuse down those tubes, reaching more cells deep within a larger body. It literally allowed their bodies to bulk up like balloons. Higher oxygen concentrations essentially inflated insect tissue, cell by cell, bypassing the typical size limitations of their respiratory system. Without this atmospheric boost, their internal plumbing just couldn't keep up with the demands of a massive body. But oxygen wasn't the only ingredient in this recipe for gigantism. Toss in a globally warm, humid climate that fostered vast, swampy forests, especially during the Pennsylvanian epoch of the Carboniferous. These weren't your average woods. They were sprawling, dense jungles of giant club mosses, towering ferns, and horsetails, creating an endless plant buffet. This lush environment provided abundant food resources and ideal habitats for these burgeoning arthropods. And here's another crucial factor. The skies were relatively empty of predators. For roughly 70 million years, before the evolution of birds, there were no aerial vertebrate predators to contend with. Early amphibians and reptiles were just beginning to test terrestrial life, meaning large insects had little to fear from above. This absence of significant aerial threats meant that size was often the best defense, and there was little selective pressure to remain small and nimble. This combination of high oxygen, abundant food, and a lack of predators created an evolutionary green light for gigantism, allowing insects to push the boundaries of their physical forms. So, who were these incredible behemoths? Let's meet some of the heavyweights that roamed, or flew, during this remarkable period. First up, the undisputed king of the Carboniferous skies, Meganeura. Think eagle meets dragonfly, but with a wingspan that could stretch an astonishing 65 to over 70 centimeters. That's about 28 inches. While often called a giant dragonfly, Meganeura was actually a griffinfly, a distant relative. It wasn't just big. It was a formidable aerial predator. With large, bulging eyes, Meganeura had excellent visual acuity, perfect for spotting prey from a distance. It hunted by slamming mid-air prey against its spiny legs, much like modern dragonflies do, then munched on anything smaller than a sparrow, including other insects and even small, newly terrestrial amphibians. Imagine this creature, a veritable terror of the ancient air, dominating the skies long before birds or bats ever took flight. Next, we descend to the forest floor to encounter Arthropleura. This isn't just a big millipede. It's the largest known land invertebrate to have ever lived. Reaching lengths of up to 2.6 meters, over 8.5 feet, and a width of 50 centimeters, about 20 inches, Arthropleura was truly colossal, roughly the size of a small car or a school bus in length. Despite its nightmare-inducing length and armored appearance, this segmented giant was likely a gentle herbivore. It bulldozed through the undergrowth, vacuuming up fallen seeds, fruits, plant debris, and leaf litter like a living compost roller. Evidence from gut contents and fossilized feces suggests a diet rich in plant matter, including pteridophyte spores and lycophytes. Its sheer size, however, meant it probably had few, if any, natural predators. Finally, lurking in the shadows, we have Pulmonoscorpius kirktonensis. This wasn't some tiny garden scorpion. It was a predatory arachnid that could reach an estimated length of 70 centimeters, about 28 inches. Armed with powerful pincers, likely the size of small pliers, and venom calibrated to liquefy other bugs, this was a creature you definitely wouldn't want to find in your tent. Pulmonoscorpius was an active, visually oriented diurnal predator, hunting smaller arthropods and perhaps even early small tetrapods on the forest floor. Its proportionally large eyes suggest it relied heavily on sight to stalk its prey. These three, Meganeura, Arthropleura, and Pulmonoscorpius, formed a trinity of aerial predators, terrestrial recyclers, and formidable ground hunters. They weren't alone either. Other large insects included Mazothyros, another giant flying insect with an estimated wingspan of around 56 to 85 centimeters, known for its beak-like mouthparts used to pierce plant tissues and suck fluids. Giant cockroaches and large mayflies also thrived, contributing to this incredible biodiversity of colossal arthropods. This golden age of insect gigantism, however, couldn't last forever. Like all empires, it eventually faced its decline. The fall began as the planetary thermostat started to dip, and Earth's climate underwent significant changes. Vast swamps dried up. The once expansive forests began to shrink, and crucially, atmospheric oxygen levels started to slide, eventually falling below 25%. For insects, this was a critical blow. A dragonfly built like a laptop can't efficiently squeeze enough air through its tracheal tubes when oxygen is scarce. Every breath became a metabolic marathon, and the larger the body, the more challenging it was to get enough oxygen to sustain life. The very system that allowed them to become giants now limited their survival. Meanwhile, a new player was entering the evolutionary arena: early reptiles. These creatures cracked a crucial code for terrestrial survival: the shelled egg. Unlike amphibian eggs, which needed to stay in water or moist environments, the amniotic egg had a protective, often leathery or calcified shell. This innovation allowed reptiles to lay their eggs on dry land, freeing them from aquatic environments and enabling them to wander inland, away from water bodies where amphibians were still largely constrained. This meant they could exploit new niches and resources. And what did they find inland? Big, juicy, slow-moving protein sticks. Those giant insects and other large arthropods that had previously enjoyed a relatively predator-free existence. Gigantism, which had once been a superpower, rapidly turned into a liability. A huge body, once a deterrent, now made them easy targets for these increasingly agile and diverse vertebrate predators. Over a few million years, evolution began to trim wingspans and thicken armor. But the glory days of insect giants were undeniably over. By the time dinosaurs appeared in the late Triassic period, oxygen levels continued to yo-yo, but they never quite regained the supercharged highs of the Carboniferous. The Mesozoic era saw insects continue to thrive, but generally at much smaller sizes. The ecological landscape was shifting dramatically, especially in the skies. Then, about 150 million years ago, a revolutionary new group burst onto the scene: birds. The evolution of birds marked a pivotal turning point. These feathered, flying vertebrates were agile, fast, and highly efficient predators. They turned the aerial food web upside down, introducing intense new selective pressures on flying insects. A beetle that might once have outgrown a mouse now survived best by shrinking, becoming more maneuverable, hiding effectively, and breeding fast. Birds, through their sustained and often strong predatory impact, became a significant evolutionary force. They favored smaller body sizes and increased agility in their insect prey, influencing traits like camouflage, defensive behaviors, and reproductive strategies. Even if oxygen levels occasionally rose again, as they did in some periods, the presence of these new, highly efficient aerial predators kept insect sizes in check. Insects essentially swapped brawn for brains, or more accurately, for highly developed sensory antennae, complex behaviors, and incredible adaptability. They diversified into the astonishing kaleidoscope of tiny forms we see today, mastering camouflage, mimicry, and complex social structures. The age of giant insects had given way to an age of incredible insect diversity, driven by new environmental pressures and a sky now dominated by birds. The brief, spectacular empire of giant insects might be long gone, but their legacy isn't lost to time. It's preserved for us in stone, in the remarkable fossil record. Paleontologists meticulously study fossilized wings, intricate trackways left on ancient mudflats, and even molted exoskeletons to piece together this prehistoric puzzle. Modern science uses incredible tools to understand these ancient organisms. Researchers employ CT scanners to model the internal tracheal volume of fossilized insects, allowing them to precisely calculate the maximum size an insect could achieve under different atmospheric conditions. These studies consistently prove a crucial point. Modern oxygen levels simply won't support a dragonfly the size of a crow, or a millipede as long as a car. The physics of diffusion and the mechanics of their respiratory systems set a clear upper limit on their size in today's atmosphere. Museum displays around the world keep the wonder of these giants alive, reminding us that Earth's rulebook for life isn't static. It rewrites itself whenever the atmosphere, climate, or the dominant predators shift. The giant insects of the Carboniferous and Permian were a unique product of a perfect storm of planetary conditions: high oxygen, lush vegetation, and a relative lack of aerial competition. Their existence serves as a powerful reminder, almost a warning, that no reign, not even ours, is permanent. Life is incredibly adaptable, constantly evolving in response to its environment. The Age of Dinosaurs often gets top billing in our imaginations, but the Age of Giant Insects proves that life can scale to truly comic and terrifying proportions when the air itself acts like a performance drug. High oxygen levels unlock the skies for creatures like Meganeura, allowing wings to stretch to their engineering limit. The endless plant buffets fueled the massive bodies of herbivores like Arthropleura, and the absence of powerful aerial predators meant that big was beautiful and safe. But as oxygen levels ebbed and sharp-toothed, egg-laying vertebrates arrived on the scene, the titans of the insect world deflated. They left behind only echoes in stone and the occasional, modest flutter of a modern dragonfly, a mere shadow of its colossal ancestor. Next time you swat a fly, remember its lineage once terrorized the planet, hunted small amphibians, and dominated the ancient skies. Then perhaps, thank your lucky stars that it's only housefly size today.